substitution reaction, and previously we have discussed the mechanism of SN1 and SN2 reaction, and also about their stereochemical point of view. The reaction has been analyzed from the stereochemical point of view, and now we are coming again. Now we will discuss about the factors affecting SN1 and SN2 mechanism. Factors affecting SN1 and SN2 mechanism. Our first point is the polar effect. This polar effect, this comprises this inductive effect. Number 2, mesomeric effect. Resonance effect. And hyperconjugation effect. All these effects are mainly the combination of all these effects are called the polar effect, and it is found that this primary carbocation, primary alkyl halide, these undergo SN2 mechanism due to this polar effect, and secondary alkyl halide, they can undergo reaction either by SN1 or SN2. Both is possible for them. While for tertiary alkyl halide, these SN, they exclusively maintain the SN1 mechanism. So these are the field effect, or these are the polar effect rather, that this inductive effect, mesomeric effect, resonance effect, as well as this hyperconjugation effect, they allow the primary alkyl halide, or they force the primary alkyl halide to undergo SN2 pathway. Next, secondary alkyl halide, they may either undergo SN1 or SN2. That depends upon some other factors also that we will come later. And tertiary alkyl halide exclusively undergo SN1 pathway. Next, point number 2 is steric effect. Now, as the size of the alkyl group increases, the steric effect also increases, and as a result, these alkyl halides which have a large alkyl group around it, they experience a steric hindrance when they undergo SN2 pathway, that is in the transition state. In the transition state, there become which is called steric crowding. That is, more and more alkyl group are coming in, they are present in the transition state, that become much more sterically hindered, and its stability get lost, and they become less stable, and that is why we found that this steric property, or this that we call the bulkiness of this bulky groups reduce the stability of transition state, and we found that this methyl group, it is less bulkier than primary alkyl halide, which is less bulkier than secondary alkyl halide, which is less bulkier than tertiary alkyl halide. So the steric hindrance is experienced maximum in case of tertiary halide and minimum in case of methyl group, and then it will come to primary halide. So sometimes there also have presence of this neopentyl. Suppose in case of another example is in neopentyl group. Here also we found that though this alkyl halide, that carbon containing the halogen has hydrogen but it has also a big group, tertiary butyl group, which is, let it down, C H C CH3 CH3. So this is in case of this compound, though this carbon is attached with hydrogen, 2 hydrogen and 1 alkyl halide, but these are not much bulky groups, but here we have a tertiary butyl group which is much bulkier here. So these also experience steric hindrance in the transition state. So this type of alkyl halide, they undergo preferentially SN1 pathway. Although they have hydrogen, 2 hydrogen here, but due to this presence of this tertiary butyl group, and that tertiary butyl group creates much more hindrance in the transition state. So this SN1 pathway is preferred here. So this is called the neopentyl alkyl halide. Now next point is Next point is number 3 is nature of living group. Now, in case of SN1 pathway, SN1 mechanism, which you see that more is the stability of the living group, more will be the ease of formation of this carbocation. That means if we see that RCl or Rx, suppose, if X is easily removed from this alkyl group, and then this carbocation and X minus is formed, and if this X minus is more stable, more easily this can be released from this alkyl group, and more easily this carbocation will be formed. So stability of this alkyl group is stability of this living group is a major factor in case of SN1 reduction, and we found that the order of this stability of living group is like this way: CF3 S double one O minus. This is greater than Br which is greater than CH3 O minus, which is greater than C6H5 or this O double one O minus, which is greater than CH3 S double one O minus, which is greater than I minus, which is greater than Br minus, which is greater than CF3 CO minus, and which is greater than CH3 COO minus. So what we see that this CF3 SO3 minus, this has the maximum stability, and it is a most suitable living group, and it can easily produce this alkyl carbocation, while here this CH3CO minus, this is the least favorable living group, and it will not easily produce this alkyl carbocation. So this order of living group indicates that which one will lead to the which pathway, that is S1, which one will favor the SN1 pathway most. Next point is nature of nucleophile. Nature of nucleophile. It is observed that the strong nucleophile that favors SN2 pathway, while weak nucleophile favors the SN1 pathway. So what we see is that the strength of this nucleophile, order of strength of nucleophile, that is pH S minus, which is greater than Cn minus, which is greater than I minus, which is greater than ETO minus, which is greater than OH minus, which is greater than Br minus, which is greater than PHO minus, and which is greater than Cl minus, and which is greater than N3N. So we find that this nucleophile, it will favor the SN2 reaction, while this in this case this will favor the SN1 reaction. Next factor is neighboring group participation. Number 5 is neighboring group participation. Now in this topic we are discussing that some groups which is acts as a neighboring group also participate in the substitution, nucleophilic substitution reaction, and these groups are mainly COO minus X stands for halogen, OH group, OCO group, and pH group. These are the etc. These are the neighboring group which also take part in nucleophilic substitution. For example, suppose if we take for example halogen as neighboring group. In this case, we found that C, or compound like this type of compound, HCH3 C CH3 OH, and this hydrogen is here it is a dotted one, this one, and here is a bromine. Now this bromine, this lone pair of electron, this can act as a nucleophile, and this can attack here, and this OH minus leaves. And we found that it is a intramolecular SN2 reaction. That is, reaction is taking place within the molecule. Within the molecule, the bromine is as a neighbor group acts as a nucleophile. And we found a cyclic bromonium ion is formed here. This is Br plus, and hydrogen, and here it is methyl CH3, and we have one Br minus. Now this Br minus, this can attack in this carbon or in this carbon. So we will get this is cyclic bromonium ion, and this cyclic bromonium ion, this is an intermediate is formed, and this, when bromine Br minus attack either in this carbon or in this carbon, we get two products. One is C here plus C which CH3 Br we have H CH3. So these two are the racemic mixture of racemic mixture of dibromo of dibromo derivative of dibromo compound. This is a example of our neighboring group participation, where this lone pair is attacking as a nucleophile, and here a cyclic bromonium ion is formed, and this bromine can now this Br minus can attack from either side, from this side or this side. So we are getting this dibromo derivative. Similarly, we can take another example. Number 2, this is the acetoxyl group. This can also act as a neighboring group. Now if we have this compound, this is oxygen, this CH3 double bond O, and when this pi bond is attacking here we have one Br also, and this Br is removing, and this Br is leaving here, and we are getting this compound. CH3 and this carbon is positive. Now this is minus Br minus. Now this positive, this carbon is positive, and it is from water, it is taking OH minus, and it produces this compound. This CH3, this is OH, and this is this O, and this is joined here, and this compound, this hydrogen, it is moving here, and this bond is broken. So what we get here is OAC and OH. So this is the acetyl group. This is the product. This product is formed by the negative by neighboring group participation of this pi electron, which is attacking here. So this type of reaction is also affecting the, actually this type of neighboring group can also sometimes hindered the reaction. That means there may be some side product of this type of reaction, in this type of reaction, that due to this participation of this neighboring group. Our next factor is polarity of solvent. Here, this we found that in the protic solvent, this SN1 reaction is SN1 mechanism or SN1 reaction favors, because in this protic solvent, in the SN1 reaction, this carbonium ion is generated, carbocation is generated, which is gets stabilized in protic solvent. While such protic solvents are CF3 COOH, H2O, CH3OH. These are the protic solvent which are useful for SN1 type of mechanism. While in aprotic solvent, this SN2 mechanism are favored. This in a aprotic solvent, SN2 mechanism is favored, because in this case, in case of SN2 mechanism, this strength of the nucleophile is a factor, and in the aprotic solvent, this strength of nucleophile is increased. So in such case, aprotic solvents are examples are CH3 COCH3, CH3 C11S, CH3 S11O CH3, that is thioacetone, and HC11O N CH3 whole 2. This is NN dimethyl formamide, and these three are aprotic solvent, and they favors the or they supports the SN2 reaction, SN2 mechanism. Now, besides these factors, we have to remember some other points here. Number one is this benzylic and allylic compound. They undergo SN1 pathway because of the stability of this corresponding carbocation. If you say the benzylic carbocation, benzylic chloride, this is benzyl chloride, CH2Cl. This on when dissociates, this gives us this compound, CH2 plus, and this CH2 plus this is further react with suppose CH3OH, and this lone pair is attacked here, and we are getting this compound CH2OCH3, and this compound is rather ether. This is ether, and this compound is formed due to the resonance stabilization, because this bond pi electron is can shift from here, and this carbocation is stabilized, gets resonance stabilized like this way. This is plus, and this in this way it is further resonating, and this positive charge is delocalized in the ring, so which increases the stability of this carbocation, and as a result this solvent can attack here, and we are getting the SN1 substituted product. But in case of this compound, this dissociation of to produce this carbocation, this is highly unstable. This compound is highly unstable, and this carbon is sp hybridized, and so this due to the loss of atomicity, this species is highly unstable, so no such substitution reaction is taking place here. So phenyl carbocation does not undergo any substitution reaction or any further reaction, but this benzylic carbocation undergo reaction. Similarly, in case of allylic carbocation, suppose if you have this compound H2C11CH CH2Cl, this on dissociation gives H2C11CH CH2 plus, and this further react with water to give us actually this also get resonance stabilized by this way, and CH2CCH11CH2 plus, and here from water electrophilic attack from the water molecule, we are getting this compound HOCH2CH11CH2. Now this compound is formed, but in case of vinyl chloride, this is our allyl chloride, and in case of vinyl chloride, you can see that this on dissociation gives us this compound CH plus, plus Cl minus, but this carbocation is very unstable, very unstable. So this vinyl chloride does not undergo therefore any sort of substitution reaction. So this type of restriction or restrictions or exception, we can say better to say exception, are to be remembered here. In case of phenyl carbocation, benzyl carbocation, and as well as in allyl carbocation and vinyl carbocation. This compound is vinyl chloride. Vinyl chloride, and this is vinyl carbocation.